In this video, I'm going to be explaining how single and multi-qubit gates work in quantum computers and how they differ from logic gates in classical computers. So, analogous to how classical computers are built from wires and gates, quantum computers are built from wires and quantum gates. So, again, classical computers have wires to transport information throughout the computer, and they have logic gates to manipulate this information. The only non-trivial single-bit gate in a classical computer is the NOT gate, right? And so we can see it in this truth table here. If the bit's a 0, it'll take it to a 1. If the bit's a 1, it'll turn it into a 0, right? So is there a quantum analog to this NOT gate, right? Which is to say, is there some quantum gate that sends ket 0 to ket 1 and ket 1 to ket 0? The only thing is, this function wouldn't tell us what the effect would be on a state that's in superposition, right? Because we know that arbitrary quantum states can be in superpositions of 0 and 1, right? So recall, we can have, and so what will we do in that case, right? So recall our most atomic unit of information is no longer a scalar bit, right, in a quantum computer, but it's a two-dimensional complex valued qubit, so a vector. And I'm going to quickly define what a linear operator is, because we're going to need this definition in a moment. So this definition of a linear operator is if we have some vector space V over some field K and a mapping A, so a mapping A, right? So this linear operator from V to V is linear if and only if it supports this property here, right? So you can pull these scalars out and then you can distribute the operator to the individual elements of this vector space. And so we have this postulate here. So I'm not going to prove this. We're just going to take this as a given. So every quantum gate is a linear operator. So every quantum gate is, one of these mappings A that obeys this property here. So what we're looking for, right, is a linear operator. We'll call it O. That maps Hilbert space into Hilbert space. So for now, just think of Hilbert space as where these arbitrary quantum states live before we project them into a basis, into a vector that we can work with. Such that when we apply O to ket 0, we get ket 1. And when we apply O to ket 1, we get ket 0. And again, these kets are arbitrary quantum states in Hilbert space. So not yet are they, these vectors 1, 0, right, 0, 1, right? That doesn't exist yet because we haven't chosen a basis. Now, when we choose the computational basis, right, that is now when ket 0 becomes this vector and ket 1 becomes this vector. Just an important distinction. I struggled with grappling, with this idea for a very long time. So I hope, this kind of makes it a bit more clear. So now after we select the computational basis, this linear operator O can be represented as a matrix mapping ket 0 into ket 1, right, and ket 1 into ket 0. And that will automatically define what the matrix representation is. We'll call it X. So that is exactly what it would look like, right? Because ket 0 gets mapped to ket 1, and ket 1 gets mapped to ket 0. And so this is, we can see just showing us how we can apply it to an arbitrary quantum state in superposition. So we have our quantum state here. Recall, so this is our operator, right? And we know that when we apply it to this state, we can distribute it, right? Which is what we do here. And that's because X is a linear operator, so it obeys this property here. And then we can expand X into a matrix, right? And expand these kets into vectors. And we see that what has happened is that ket 0 has flipped into ket 1, and ket 1 has flipped into ket 0, exactly as we expected. Equivalently, we can also just do the flat-out linear algebra here. So we can just immediately sub in the matrix for X and the vector for ket psi, and then just that'll just flip beta and alpha, right? So that's just an equivalent way to visualize it. So for now, we're just going to be strictly working in the computational basis. So operators are going to be matrices now that we've established that we are working in the computational basis, just for clarity. So recall that for any qubit, we have this restriction that the mod square alpha plus mod square beta has to equal 1, right? Because these are probabilities at any state in the computational process. It has to be that the quantum state of our computer is the mod square of the amplitudes sums to 1. And so from this constraint falls out that every quantum gate must be unitary. So what does unitary mean? So here's the definition of unitary. A matrix U is unitary if and only if U dagger U equals U dagger equals I. So this is just the identity matrix, right? Where U dagger is the complex transpose of U. Or, just for completeness, this also extends to operators. So what is a unitary operator? This would still hold, except that this, U dagger would now be the adjoint, which is just, a generalized complex transpose, essentially. But, this definition of unitary applies to operators as well as matrices. This is just a more specific case where you're looking at a unitary matrix in which the adjoint is the complex transpose. And so it's easy to check the unitarity of X, right? Like this quantum NOT gate. We just plug in X for U. We'll see that we do get the identity matrix. And this is actually the only restriction placed on quantum gates such that they are valid. So in order to have a quantum gate, in order for a matrix to be a quantum gate, it just has to be unitary. That's all. And so some other useful single qubit gates are the Z gate, which is this matrix here. And so that leaves ket 0 unchanged and then maps ket 1 into minus ket 1, right? So it just flips the sign. And then we have the Hadamard gate here. This maps ket 0 to a equal superposition of ket 0 and ket 1, which is canonically defined as ket plus, and then maps ket 1 into this superposition of ket 0 and ket 1 with a negative relative phase, right? And that's defined as ket minus. So now moving on to multiple qubit gates. So some important multiple qubit gates on a classical computer include AND, OR, XOR, NAND, and NOR. And I'm sure you're familiar with these gates, right? On a quantum computer, the atomic multi-qubit gate is the controlled NOT gate, or CNOT gate. So what is this gate? So the CNOT gate works with 2 qubits, one serving as the control and one serving as the target. So if the control qubit is a 1, it'll flip the target, otherwise it'll do nothing. And we can see that here, right? So if this column would be our control, this would be our target. So if you have a 0, right, if we have zeros here, nothing happens to the state, right, because our control is 0. Otherwise, if we have a 1 as the control, then it'll flip the second bit here, which is what we see there. And then the effects of that gate can be represented as this matrix here. And, since this is a quantum gate, it is also unitary. In a circuit diagram, this is what the C0 gate looks like. So A would be your control, B would be your target, and you would end up with this state here, right, on the right side. This is just an XOR. So if you go back here, you can just plug in, you can just XOR these bits. You'll see that you do get the equivalent outputs. And something important in quantum computing is that unlike in classical computing, every gate needs to be reversible. So every gate needs to have an inverse and be invertible. And this fact falls out of the constraint that every quantum gate has to be unitary. And this differs from classical computing, right? Because if we look at the classical logic gate, the AND gate, right, and look at its truth table, what do we see? So what we see is that different inputs, so like these three inputs, all map to the same output. So from the output alone, we can't figure out what the input was. If we see a 0, we know that the input could have been 0, 0, 0, 1, or 1, 0. And so this fact is makes it such that AND is non-invertible. So it's irreversible. And this is a property unique to classical computers. Quantum computers must be reversible. And so there are other multiple qubit gates, but the C0 is the most important because it's the lightest weight entangling gate, which we'll see what that actually means later on. But essentially, we have this postulate here, this theorem that's been proved, and it's such that any multiple qubit logic gate can be composed from C0 and single qubit gates. So C0 gives us this universality that is so, helpful and desired when analyzing quantum circuits in a quantum computer. So I hope this was helpful. If anything was unclear, please let me know in the comments. But other than that, thank you.